Okay, so it's Tuesday, April 28th, and we're here for a Zoom class for general chemistry from Northern New Mexico College. And we're interested today, we're going to start with section 16.2, polyprotic acids. Okay, and polyprotic acids are necessarily weak acids. At least a polyprotic acid contains more than one acidic proton. For example, sulfuric acid contains 2 acidic protons. Phosphoric acid contains 3 acidic protons. Okay, now removal of the first proton in the case of H2SO4, if we write this out, is a strong acid. Here, let me just start that over again. So H2SO4 sulfuric acid plus water, one-way street here, not an equilibrium. H3O plus HSO4 negative. So this H2SO4 is a strong acid, okay? But the conjugate base here itself contains an acidic proton. So it likewise can dissociate. But in this case, removal of the second proton is a weak acid operation. So it is an equilibrium. Okay. Now, does this mean that in every polyprotic acid, in other words, an acid that contains more than one acidic proton, is the removal of the first proton always a strong acid phenomenon? The answer to that is no. Right? In most cases, it's going to be, both steps will be a weak acid. For example, carbonic acid, which is H2CO3, all right? This removal of the first proton is itself a weak acid proposition. Okay, but in the case of sulfuric, it's a strong acid. Okay, so again, there's no big deal with these polyprotic acids. It's just when you're working a problem, you have to take into account removal of both protons. Okay, so at times that will affect the pH of the solution depending on the Ka. So this has, well, there is no Ka here. This is a strong acid. But if we look here, there's a Ka1 for this pink one, and then for removal of the second proton, there's a Ka2. CO3, 2 minus. So this first reaction is governed by Ka1. Okay, acid dissociation constant for removal of the first proton, and then the second one is governed by Ka2. Okay, as it works out, for any polyprotic acid, successive removal of subsequent protons becomes harder and harder. In other words, Ka1 is always much, much bigger than Ka2. Right? In the event of phosphoric acid, H3PO4, there's 3 acidic protons. Ka1 is much, much bigger than Ka2, which in turn is much bigger than Ka3. Right? So removal of the first proton is easiest, and then and we learned about this last class in chapter 15 in relationship between acid strength and molecular structure. Okay, and you were given a problem or two on that. Okay, so let's see here. And again, we can write an expression for Ka1 here. Let's do that. Let's forget about the sulfuric acid here, because the first step is, again, a strong acid event. So here I can write a Ka1 expression for here. Ka1 equals products over reactants. So H3O plus times HCO3, hydrogen carbonate minus, divided by the concentration of the free acid. All right, so there's Ka1. But I can also write an expression for Ka2 here. All right, so Ka2, again, will equal products over reactant. So H3O plus times carbonate anion divided by hydrogen carbonate anion. Okay, so, but other than that, you're going to work the problem pretty much exactly the same way. Let's see, what do we want to say here? Well, I used the two acids that are in the book here. So let's take a look at some problems here. Example 16.4. Again, I'm not going to work this one. I'm going to work exercise 16.4. And unfortunately, now if you take a look at example 16.4, we don't use the quadratic formula in either one of these, or for either the Ka1 or the Ka2. Okay, so I mean, let's just look at example 16.4. Again, I'm not going to work it out. It's already worked there for you in the book. Ascorbic acid is a diprotic acid. What's the pH of a 0.1 molar solution? All right, and then you're asked, what is the concentration of ascorbate anion? So ascorbate anion would be akin to the carbonate anion here. It comes from the removal of the second proton. Okay, and we're looking at the values for Ka1 and Ka2 there. We see that Ka1 is 7 powers of 10 larger than Ka2. So the first proton comes off relatively easy compared to that of the second proton. Okay, but nonetheless, you can set up equilibrium constant expressions, set up a nice table for Ka1, Ka2, and calculate the concentration of that ascorbate ion. Now that's what we're going to do in exercise 16.4, but we're going to see it's a little bit different here. So let me just pull this one up. This one's going to get kind of gory. Okay. I already have this one worked out. And it's going to take a while to get to the answer here, but we'll do it. And again, this is like a problem that I'm never going to ask you to do. But you should see it once, and we don't really have another problem handy. And I didn't think I had to look at a different, actually, I don't have my other chemistry books here. So we have this problem. Sulfurous acid, H2SO3. So it has 2 protons that can be removed. All right, there's a Ka1 and a Ka2. And again, we see Ka1 is 1,000,000 times, 6 powers of 10 larger than Ka2. So the first proton is going to come off relatively easy compared to the second one. And then it says, yes, what is the pH of a 0.25 molar solution of sulfuric acid? And finally, we're asked, what is the concentration of sulfate ion in the solution? All right, so we're going to have to make a nice table. H2SO3 plus H2O gives us, this is equilibrium, so double-headed arrow, H3O plus HSO3 minus. So now we're going to make a nice table here. So ice, and we're told that the concentration of the starting solution is 0.25 molar. All right, so this is 0 and that is 0. Okay, actually I was going to change different colors, but we'll leave it. So the change is going to be minus x plus x plus x. And at equilibrium, just add them together. 0.25 minus x plus x plus x. Okay? Now, we can write out an expression for the equilibrium constant here. Okay? Does everybody have this? Because I'm going to erase this. Right? Everybody has this. All right. This is going to get a little gory now. So, Ka1 equals the concentration of hydronium ion times HSO3 minus hydrogen sulfide divided by the concentration of the free acid. So we can put in the equilibrium values from the ice table, which is x times x divided by, what was it, 0.25 minus x? Yes. Okay, now, this is looking like it's going to be a quadratic because I have an x squared term here and there's going to be an x term here, right? But last class, we saw an approximation method that would tell us when we can drop this minus x. In other words, when is x much, much smaller than 0.25, right? If it's much, much smaller, then we can drop this and then we don't have to use the quadratic formula. So what was that condition? And the condition was when the initial concentration of the free acid divided by the equilibrium constant, if that's bigger than 100, then we can drop this x. We don't have to do a quadratic equation. So let's see what that is for this first ionization here. So CA is 0.25 and Ka1 is 1.3 times 10 to the negative second. And that's not going to be bigger than 100. 0.25 divided by 1.3 double E 2 negative equals 18.2. So we cannot drop this x here. We cannot drop it. We're going to have to go ahead and do the quadratic formula. Okay, it's not a big deal. Again, I will never ask you to do that, at least not on purpose, at least not intentionally. But you should see it done once. I did do this problem without doing this. In other words, dropping this x, even though this tells us it's not valid to do that. The pH was different by 5/100ths of a pH unit, 5/100ths. All right, but we're going to go ahead and do it anyway. So, just so you can say you've seen it done once. All right, so we're going to plug in, or sorry, we're going to rearrange this. So I'll bring this over to the other side. So I'm going to have 0.25 minus x times Ka1 equals x squared. Let's distribute this. 0.025 times K minus x, Ka1 minus x times Ka1 equals x squared. All right, now let's move everything to the same side. So I'm going to move this stuff over to here. So I'm going to have x squared plus x times Ka1 minus 0.25 times Ka1 equals 0. All right, equals 0. Now, you know, I do want to mention, I took a look at the problems in the back of the book. They only have 2 related to this particular example. One of them does use the quadratic formula. That's the one that has the answer in the back of the book. And then there's another one that I will assign to you. You do not have to use the quadratic formula. Okay? So we have this. Clearly, this is a quadratic equation, so we're going to need to do the quadratic formula, right? So let's go ahead and do that. Remember that X here is equal to the hydronium ion concentration. I'm going to leave that last line there because we're going to need that. All right, so the quadratic formula is X equals negative B plus or minus the square root of B squared minus 4AC all over twice A. Okay, here, let's make it lowercase a. Okay, so we can go ahead and plug in. Negative B is negative Ka1, right? Remember, A is 1, B is the coefficient on X, which is Ka1, and then here's C. Okay? So negative Ka1 plus or minus the square root of B squared. Again, B is Ka1. So Ka1 squared minus 4 times A, which is 1, the coefficient on X squared, times C. C is this whole thing right here, and it's negative. So C is negative 0.25 times Ka1. Okay, all over twice A, but A is 1. All right, now I'm going to pick a different color for the next line. So now we'll plug the value in for Ka1. Right, and Ka1 again was 1.3 times 10 to the negative second. I'm going to put that as a decimal, which is 0.013. All right, so negative 0.013. Right, now my lines are kind of cramming together. You should not do that. So that's why I'm picking a different color here, because I don't have a lot of room to work with. Plus or minus the square root of B squared, which is 0.013 squared minus 4 times 1 times negative 0.25 times Ka1, which is 0.013, divided by 2. Okay. All right. Actually, I just want to okay. Let's work this out. Let's just simplify things a little bit here. Pick a different color. So negative 0.013 plus or minus the square root. Now, what's this B squared? 0.013 squared is 0.000169. All right, here I have a negative and here I have a negative. Does everybody see that? So this is going to become a positive term now. A negative times a negative is a positive. Okay? All right. I'm going to put this into my memory, store 1. And let's see. 4 times 0.25 times 0.013 equals 4 times 0.25 equals times 0.013 equals equal to 0.013. 4 times 1/4 is 1. All right, all divided by 2. Okay, does everybody have that? All right, right, now I'm not going to erase this. I actually went out and got my other board. All right. So let's see here now. Hopefully I haven't screwed anything up. I'm just trying to think of a way to do this. Actually, I'm going to use the smaller board. Now you see why I don't want to give you one of these quadratics. Okay, so let's calculate this out. So add that and recall 1 plus, this should be 0.013. 4 times 0.25 times 0.013 equals, yes, this should be 0.013. Glad we caught that. I have this worked out on the computer behind me. So 2. So recall 1 plus recall 2. Recall 1 plus recall 2 equals. All right. Now, that's going to turn into negative 0.013 plus or minus 0.11476 divided by 2. Okay? Now, remember, that's what X is equal to, the hydronium ion concentration. Okay? Now, I'm going to put this into my third memory. Okay, now, take a look here. There's 2 answers, right? There's this plus or minus this square root here. That's this square root. Okay? Now, but notice here, X is the hydronium ion concentration. It must be a positive number. It must be a positive number. Now, if I take 0.013 and subtract 0.114, that's going to be a negative number. That answer has no physical meaning. No physical meaning. Only the positive root makes physical sense. So our answer is going to be this negative plus this 0.114 divided by 2. So let's go ahead and do that. 0.013 negative plus recall 3 equals divided by 2 equals. And I get X equals 0.050878. Let's see, is that what I had here? Yes, that is. Okay, so we did it right. So this is the hydronium ion concentration. The hydronium ion concentration. We were asked to find the pH. Well, the pH is equal to negative log of hydronium ion concentration. All right, which is negative log of 0.050878. Right, which is equal to, if I remember correctly, 1.29. 1.29. Okay, which is in fact the answer in the back of the book. Okay, now if we had not made that approximation? Ca over Ka. All right, we saw that the starting concentration, 0.25 molar of the sulfuric acid, 0.25 divided by Ka1 was only equal to 19.2. So we said, well, we have to do the quadratic. What if we had said, no, I don't want to do the quadratic, I'm going to drop that x, right, in the denominator. In the initial expression for Ka1, if you look back, we had, here, let me write it on this other board here. So how different an answer would we have gotten, right? So we had Ka1 equals H3O plus, equals x times x divided by 0.25 minus x. What if we had said, I'm going to forget about that x there, and I'm just going to say Ka1 is approximately x squared divided by 0.25. How different would my answer have been? And it turns out it would not have been a whole lot different. Instead of a pH of 1.29, we would have had 1.24, right? 1.24. So not a whole lot different. Okay? Any questions there? All right. Again, it's nothing that we didn't do last class. It's just this time we had to do a quadratic equation, whereas last class we did not have to do that. We're still not done here. We're still asked to find the concentration of SO3 2 minus. Right, so we've only answered the first question. All right, any questions on it to this point? Any questions? All right, let's look at the other one, where we have to find the concentration of the sulfide anion in solution. And for that one, we're not going to have to do the quadratic equation. So, but we are going to have to set up another ice table. And so this is going to be for Ka2. All right, plus H2O gives us H3O plus SO3 2 minus. Okay, now remember, this was the conjugate base from Ka1, right? That was the conjugate base from Ka1, but it has a second proton, so it also can undergo dissociation, an acid dissociation reaction. We have to set up another ice table. Now, what do I do with my calculator? There it is. All right, now, our starting concentrations here are going to be what? They're going to be these starting concentrations are going to be the equilibrium values from Ka1. So that was 0.050878. That's also the concentration of this, 0.050878. Remember, that was just X that we solved for, right? Just X that we solved for. Let me just bring up. So as we're doing each step, I can check and make sure that we have the right answers here. All right, and there's no sulfite anion at the beginning. Does everybody understand where these numbers come from? These are just the equilibrium values from the previous step, from Ka1, right? That was the value for X, right? The value for X, right? Remember, in the first dissociation step, these two were on the same side. Let's write out what that was from the first step. All right, you don't need to write this down. Okay, but here you see HSO3 and H3O plus are on the product side, right? So when we set up that ice table, the equilibrium step, this was X and this is X. This is the value for X. Okay, so that's where these 0.05s came from. All right. Now, again, at the beginning, there is no sulfite anion. So what's the change? We're going to call this minus Y. We'll use X for this Ka1 and y for the second dissociation. This will be plus y, this will be plus y. Okay, so what's the equilibrium? 0.050878 minus y, right? This will be 0.050878 plus y, and this will be plus y. Okay, I certainly have gone out too many digits here, but that's okay. Worry about it at the end. Okay, everybody have this so far? All right, so again, it's just another ice table. It's not a big deal. All right, I'm going to erase it and set up the expression for Ka2. And hopefully I can do this without having that information in front of me. So let's have a look here. Ka2 equals H3O plus times sulfide anion divided by hydrogen sulfide anion. All right, so now we can plug in the equilibrium values from our ice table. Again, anytime you have a question or comment, do not hesitate. So Ka2 equals, all right, if I remember correctly, this was 0.050878 plus y. And this was y, and this was 0.050878 minus y. Okay? Now, looks like we got another quadratic problem. But let's check this Ca2, or Ca divided by Ka2. Let's take a look at that. And so we'll do this on this little board here. Okay, everybody has this here? I'm not going to erase it yet, so if you need it, it'll still be there. So we're just going to check that. We want to check and see if it's valid to drop this minus y and this plus y. All right? In other words, is y much, much smaller than 0.0508? Right? And we can do that, as we learned in the last class, by looking at the concentration of A divided by Ka2, which is equal to, now, we don't want the original acid. We want the starting concentration of HSO3 minus, right? Because that was our starting acid for the second step. And that concentration is 0.050878, right? So we don't want the 0.25. That was the concentration of H2SO3. And Ka2 here out of the book is 6.3 times 10 to the negative 8. And that's going to be way bigger than 100. This is 10 to the negative second divided by this. So it's going to be like 1,000,000. So let's look. So recall 1 divided by 6.3 is 10 to the 8th negative second scientific. Yeah, so it's 800,000. 800,000. So it's way, way bigger than 100. Way, way bigger than 100. So it's going to be okay to drop that plus or minus y. Right? Everybody has this? Again, understand this, what we did here, because it's going to tell you whether or not you need to do a quadratic equation. All right. So since that was way bigger than 100, I can drop this plus y, drop that minus y. So we'll go Ka2 equals 0.050878 times y divided by 0.05. And looky here, something pretty cool. This cancels, right? This is identical to this. So this all cancels. That's equal to 1. So underneath, let's write what's left. Ka2 equals Y. And what is Y? Y, if you look at your ice table, was the concentration of sulfite anion, which is what we were after. Okay, and notice it's equal to the concentration of that at equilibrium condition is just equal to its own Ka. It's equal to its own Ka. And if we take a look here in our textbook, and sit down here for a moment, right under that exact exercise there in the green, it's the last thing on page 554. The concentration of the ion, A2 minus, there it is, 2 minus, is equal to the equilibrium ionization constant, Ka2. So the concentration of sulfide anion is 6.3 times 10 to the negative 8. 6.3 times 10 to the negative 8. This is a very, very powerful relationship because it actually saves you. If all you're after is the concentration of sulfide anion, okay, A2 minus, you don't even have to do that ice table. You don't have to do the second part of the problem. You don't have to do any of that. All you got to do is just say, oh, it's equal to the concentration. It's equal to the value of Ka2. It's equal to the value of Ka2. Okay? Any questions there? Again, this is a very, very powerful relationship. Very powerful. Okay? So I'm going to give you one of these. I think it's problem 48. But you don't have to do that quadratic equation for the first dissociation. Okay, the Ka1 is sufficiently small compared to the starting concentration that you won't need to do it. Okay, any questions here? We use after class just to do one problem here. Okay, but it's good that you saw a quadratic equation problem. It's really not that difficult. It can be a little tedious. You got to be very, very careful. And it was good for you to see how this worked out. That again, everybody understands that Y, if you look at this second ice table we did, Y was the concentration of SO3 2 minus. All right. So the second conjugate base. The second conjugate base. Okay. Any questions? All right, we'll move on then. So let me erase this. And well, this chapter is on weak acids and weak bases. We really have not spoken about weak bases yet. Right? It seems like weak acids always get the lion's share of the discussion. Right? But weak bases exist also. So let's take a look here. And well, we'll use the one in the book there. So ammonia plus water, ammonia is a weak base, gives us NH4 plus hydroxide ion. Okay, plus hydroxide ion. So this is a Bronsted-Lowry base, NH3 is. I want to point out one thing to you here. The bases we had talked about in the last chapter were all metal hydroxides. So when you wrote a dissociation reaction for them, you did not need H2O. It was just written like this. So for the metal hydroxides, the dissociation reaction is written as in this red. Okay, but for these nitrogen-containing weak bases, okay, the dissociation, the ionization reaction for the weak base is a reaction that includes water, right? Because the base has to pull a proton off of the water, right? So here's the conjugate acid, there's the conjugate base of water. Okay, we good here. Now we can go ahead and set up, let's erase what's on the bottom here. We can go ahead, just like we did before, and we can set up an equilibrium constant for this reaction. Products over reactants, as always. Products over reactants. Okay, so there we go. All right, same as with any of our reactions. Again, we leave out the water because it has an overwhelming concentration compared to the other reactants and products. Okay, and if we take a look on page 556, we see at the top there, we see a little table with the base ionization constants for a number of weak bases. Notice they are all nitrogen containing bases. So what's the essence? Why are these nitrogen containing compounds? What do they function as bases? And if we take a look here, this reaction of methylamine with water, we see that the essence is the nitrogen, excuse me, the nitrogen on the methylamine contains a lone pair of electrons. That lone pair of electrons can pull one of the protons off of the water. All right, that leaves a protonated methylamine and a hydroxide anion. Right? So the solution of methylamine will be basic. It will be basic. Okay, and then they go on to tell us here, many drugs and plant substances are bases because they have these nitrogen containing compounds. Now, here's the thing that it's just of interest. You don't need to know this to solve any problems. Often a prescription or over-the-counter drug is the salt of a base because the salt, since it's ionic, is much more soluble in water than the free acid or the free base. Okay, so quite often these drugs are presented to us as ionic salts. This is also true for a lot of vitamins. If you look at the table of content or ingredients on some food, it will say like contains sodium ascorbate, or why not ascorbic acid? Ascorbic acid is not as soluble in water as sodium ascorbate is. Or thiamine, thiamine is generally presented as an ionic salt, if I remember correctly, vitamin B. Okay, now let's take a look at exercise 16.5. Do we have any questions? Any questions? Whoa, what happened to everybody?
I'm here.
My screen,
Here.
Everybody's there? Does my screen disappear? I hope it's still recording. I sat down, I wasn't facing the screen, and all of a sudden my background is on my computer monitor. Okay, hopefully
It says it's recording.
Okay. Although for one of the intro classes last week, it recorded, but it was just a blank screen the whole time. I'm still trying to figure out what the heck happened there. I'm thinking maybe I didn't pin my camera to the video. Okay, so let's look at exercise 16.5. Quinine is an alkaloid or naturally occurring base, okay, used to treat malaria. So we've all heard this in the news a lot lately, right? Hydroxychloroquine or chloroquine that some people have been touting as a treatment for this coronavirus infection. All right, so we're given a starting concentration and it has a pH of 9.84. Okay, and again here, the basicity of alkaloids is due to one of these nitrogen atoms with its lone pair of electrons that picks up protons from water, right? As do all those bases in table 16.2 at the top of the page. Okay, and we're asked, so what's the value of Kb for quinine? We're only given two pieces of information. We're giving the initial concentration of the quinine solution that was made up and the pH of the solution. So how are we going to get Kb for quinine? Well, let's take a look. Now again, I have this one worked out, but let's see if I can work it without. So this will be our quinine, HA, plus H2O gives us H2A plus OH minus. Okay, so it's stealing a proton from the water, OH minus. All right, we're told what the pH is, right? And we know that the hydronium ion concentration is equal to 10 to the negative pH. 10 to the negative pH. So let's get what the hydronium ion concentration was. And the pH again was 9.84. Which is equal to, get the calculator out, and clear all my memories, 9.84 negative second 10x. And I get 1.4, and again, I'll worry about the significant digits later on, times 10 to the negative 10 molar. And we expect the hydronium ion concentration to be rather small because this is a basic solution, right? It's a basic solution. So the hydroxide ion concentration should be around 10 to the negative 4, right? Because hydroxide ion times hydronium ion has to equal 10 to the negative 14. All right, so I'm going to leave this in my memory on my calculator. Actually, I'm just going to pull up the other little screen here. So now we know what the hydronium ion concentration is. From the expression for Kw, we can calculate the hydroxide ion concentration. All right, and again, if you don't understand something at any point, you guys need to speak up. All right, so let's take a look. Kw equals hydronium ion concentration times hydroxide ion concentration. Right now, what do I know here? I know that that's 10 to the negative 14th. I know that because we just calculated it. And I don't know that. Okay? Again, it's always wise to check off what you know and what you don't know. So let's rearrange this and solve it for hydroxide ion concentration. So Kw divided by H3O plus equals hydroxide ion concentration, which is equal to 10 to the negative 14 divided by, what was that? 1.445 times 10 to the negative 10. All right, and that is equal to, get out the calculator, I have this in my first memory. So 1 double E 14 negative divided by, recall 1 equals, put it in scientific notation, and I get equals 6.92 times 10 to the negative 5th molar. And I believe we were actually asked to calculate we're actually asked to calculate Kb, right? But we needed to do this. We needed to do this, okay? So let's remember that number. I'm gonna put it in my memory. I wanna ask a question here. Does anybody see why we had to calculate the hydroxide ion concentration? Does anybody see why that is? Remember, we're after Kb, right? We're after Kb. Well, let's take a look here.
Isn't that what you plug into the equation?
Yes, into the equation for Kb, yes. Very good. So let's set up, we have this equation. Let's set up our ice table. What was the starting concentration? 0.0015. 0, 0. Right? The change is minus x plus x plus x. So this is 0.0015 minus x plus x plus x. But I know what x is. I just solved for it a moment ago. Right? X is the hydroxide ion concentration. But we just calculated what the hydroxide ion concentration is. So I know that. So I can go ahead and plug in. I'm going to write small here.
Girls.
Sorry? Everybody okay? I shouldn't be calling this H. Usually that we think of that as an acid. But anyway. All right, so I know these two are the same. And I just calculated it a moment ago. So 6.92 times 10 to the negative fifth squared, because that and that are the same. Here, actually, let's take it from the ice table. Let's not jump ahead of ourselves. Whoa, let's plug it in from the ice table. All right, so KB equals x times x divided by this. Right? And now we can just go ahead and plug in the numbers. Okay? So this one, so this is just x squared. So 6.92 times 10 to the negative fifth squared divided by, now again, I picked a different color so that you could, but you guys should not cram all your stuff together. All right, I ran out of room, so I don't have any choice here. All right, but you shouldn't be cramming everything together. Then divided by 0.0015 minus x, which is 6.92 times 10 to the negative fifth. That's our KB. All right, so now I've run out of room. So I'm going to bring it up to here. And KB is equal to, just do this in red on the calculator. I'm going to do the denominator first because it's got two terms. I'll put that into memory, and then I'll do the numerator divided by the denominator. Right? That's a useful thing to do when the denominator has two terms. All right, so 0.0015 minus recall 1, because I have this 6.92 in my second memory, or first memory, equals. I'm going to put that into my third memory. So this denominator is in my third memory. The numerator, the 6.92 is in the first memory. So recall 1 squared divided by recall 3 equals. And I get 3.35 times 10 to the negative sixth. And let's see if that's what we have here. That was exercise 16.5. Yes. Okay, so that's the answer in the back of the book. Okay, again, all these problems, they're just some variation of an ice table. All these weak acid and weak base problems, they're just some variation, some twist off of an ice table. Okay, any question here? Any question? So you'll get a problem that's similar to this one. Okay? All right. Let's see, what time we at here? 5 o'clock. So we still, oh, we only got 15 minutes. So example 16.5 is just like we did with a weak acid, except it's a base. Okay, so I'm going to do the exercise that follows it. Are there any questions on this? My advice to you when you're working these, because you notice they're kind of long problems for us, right? We're used to doing much shorter problems, all right? Again, just do one problem on a sheet of paper. Have everything sectioned off. If you need to draw boxes around stuff, all right, by all means do so. I mean, for one thing, that would help me to understand what you're doing. All right, if you need to number the boxes in the order that you did them, by all means do so. All right, so let's take a look at exercise 16.6. What's the hydronium ion concentration of a 0.2 molar solution of ammonia in water? Of ammonia in water. So let's write out the base ionization reaction. We're going to make an ice table. So the starting concentration of the ammonia is 0.2 molar, 20 molar. This is 0, that's 0. Okay? And the change is minus x plus x plus x. At equilibrium, 0.20 minus x plus x plus x. Hopefully by now you feel somewhat comfortable making these ice tables. Okay, so now we can set up an expression for Kb. Kb equals products over reactants. And let's see, what do we ask to find here? The hydronium ion concentration. So we're going to solve for the hydroxide ion concentration. And once we have the hydroxide ion concentration, we can then calculate the hydronium ion concentration using either the PPOH or the ionization constant of water, right? Okay, so let's see here. We can go ahead and plug in here from our ice table. So Kb equals, let's see, x, and this is 0.20. Oh, wait, we know what Kb is. Okay, we're okay. Now, let's plug in the value for Kb. It's in that table. 16.2 is 1.8 times 10 to the negative fifth. Okay, again, this looks like we have a quadratic, but we're going to test. Here's the starting concentration, 0.20 molar. Here's the equilibrium constant. So we're going to test that. We'll go to the small board for that. Starting concentration divided by the equilibrium constant. If it's bigger than 100, then we're justified in dropping that minus x in the denominator. So let's go ahead and do that. So the Ca, in this case it's Cb, C base, divided by Kb equals 0.20 divided by 1.8 times 10 to the negative fifth. Right? Everybody understands where these numbers come from. The starting concentration of ammonia given to us in the problem. So 0.2 divided by 1.8 times 10 to the fifth negative. What am I doing here? 0.2 divided by 1.8 times 10 to the fifth negative equals. And that's equal to 1.1 times 10 to the fourth. All right, so 11,000. 11,000. So we're more than justified in dropping this X here. More than justified. Okay, does everybody understand that? As long as this is bigger than 100, we can drop that X. So, let's see, I'm going to bring this all up here. Actually, I'm going to write it on this other board here. I'm going to write it on this other one. Just in case we need to go back to that other one. So, KB is approximately, or sorry, we plugged in the value for KB. 1.8 times 10 to the negative fifth is approximately equal to x squared divided by 0.20. We dropped that x. So now x is approximately equal to 0.20 times 1.8 times 10 to the negative fifth, the square root of all that, right? The square root, right? Moved the 0.2 over and then took the square root. Right? Everybody good there? Everybody good?
Yeah.
All right, let's get out our calculator. And 0.2 times 1.8 times 10 to the fifth negative equals, don't forget to take the square root, 1.9 times 10 to the negative third. So x is approximately, I'm going to put the digits in and we'll worry about this. Let's just do it. 1.9 times 10 to the negative third. All right. Now remember that x was the the hydroxide ion concentration. This is equal to OH minus from our ice table. Okay. Now we're asked to find the, I think it was the hydronium ion concentration. I don't know why they didn't just say the pH. The hydronium ion concentration. All right. So we know that. Well, let's go. Any questions there? Any questions? So let's go to the little board. I'm going to go crazy with all these boards. All right. I know that Kw is equal to hydroxide times hydronium concentrations. All right. I know this. I know this. I don't know this. So rearrange the equation. Kw divided by hydroxide concentration is equal to hydronium concentration. And that's equal to 1 times 10 to the negative 14 divided by the hydroxide ion concentration, which we just calculated is 1.9 times 10 to the negative third. Okay? So we get out our little calculator. And I have this in my memory. So 1 times 10 to the 14th negative divided by, recall 1, equals 5.3 times 10 to the negative 12 molar. 5.3 times 10 to the negative 12 molar. Don't forget to put a unit on it. Oh, my apartment's getting hot. And that one I don't have worked out. So we'll have to check the answer in the back of the book. And that is correct. That is correct. Okay. Yeah, I don't know about you guys, but I always get a good feeling when I work out a long problem like this, and turns out to be the right answer. Okay. All right. We only got a few minutes left. Are there any questions on this one? Again, I cannot emphasize enough. If you
Exponent.
If you remember this relationship.
Can you hear me, Raymond?
Yes.
Hello.
Go
I
ahead.
keep getting the exponent wrong. I don't know why.
Keep getting the what?
The exponent wrong. Do you know what I mean? Like, I don't know why it comes up.
Is it off by 1?
No, it's not. I'll tell you what it was. It's 10.
Here,
3.
I'll
Negative
tell you
18.
what.
I got
Tell me
negative
what.
18.
Say again.
Negative 18.
Woo.
I got 5.26.
I don't think you're putting a negative 3 here. You're not making that negative.
I am. See?
Tell me how, okay, as you're punching the keys into the calculator, tell me what you're typing.
I'm putting 1 times 10 to the negative
So you're hitting a times key?
on the, yeah. I'm not putting parentheses. It's a time.
Wait, tell me the
supposed to do
actual
the
keys,
double
the actual keys you're hitting on the calculator. So this numerator here. So,
yeah, 1
all right,
times
so
10.
1, then what's the next key?
times.
Oh, come on, Miranda. You should know not to hit a times key.
No,
You
no,
should
no,
have-
it's not me. It's not me. It's Liz. Liz, you
Oh,
need to hit
okay,
this
sorry. I thought that was
double
Miranda.
E.
Liz,
But I don't have a double E. I only have that. Look.
There's not one like up here, like mine. Do you see it?
No, watch. Look. I use the caret.
all right, so you should do 1 times 10 caret.
Right.
Then
Negative
after your
14.
caret, you should probably do a parenthesis negative 14. Try that.
Okay.
So
I'll try that.
1 times 10 caret parenthesis negative 14 close parenthesis.
Divided by 1 caret parentheses negative 3. I still get negative 18.
Well, did you do the parenthesis down here?
I did.
I just did the same thing as she did, and I got negative 18 also with the caret. But I have the double E symbol, and when I did it the other way, I did get what you got, Raymond.
Yeah,
Okay.
Liz, I hate to
I'll
tell
just
you
Google,
this. but if you're going to be a
just
science
Google a
major, you
video.
really should have a calculator with scientific notation on it. You don't have a
Okay,
key that has
Raymond.
EXP or EE on it?
EXE. I have EXE.
EX what? I don't know what that is. What kind of calculator is that? Oh, there it is,
Casio?
EXP.
This one?
EXP, yes.
Okay,
All
so
right,
press
so-
that.
So type
That's
1 EXP.
EXP.
Now on that calculator, I don't know if you're gonna type 14 negative or negative 14. We'll try it both ways. 1 EXP negative 14
Okay.
divided by 1.9 EXP negative 3.
Okay. I got it. Yay!
Okay.
Good job.
That
for me.
EXP
Cool,
key
thanks,
is your
Raymond.
scientific notation key,
Okay, cool.
okay?
Okay,
All right.
thanks.
So I'm glad we cleared that up. You gotta have
Me
a calculator
too.
with scientific notation on it. It's either EE on some calculators or EXP on other ones.
Okay.
Okay, I'm glad we cleared that up for you.
Thank you.
Now, let's take a look at, again, working these problems. You're gonna, so many of them, you're gonna set up ice tables. you're going to use this relationship here a lot, this ionization product for water, right? You're going to use that a lot because in some problems, you're going to know the hydronium ion concentration and you're asked to find hydroxide. But you know what this is, you'll know what that is. Or in this problem, you knew hydroxide. You always know the ionization product of water. You're finding the hydronium ion concentration. But again, it's setting up an ice table, setting up an expression for either Ka if it's an acid, weak acid, or Kb if it's a weak base, and then just plug it in. Remember that relationship, starting concentration divided by equilibrium constant. If that's bigger than 100, then you're justified in dropping the X in the denominator. All right? Because then that X, the change, will be much, much smaller than your starting concentration. Right? But if it's not bigger than 100, you cannot do that. You have to do the quadratic. And again, I will not intentionally assign you any problems where you have to do the quadratic. We should assign you one, but I won't. Let's finish here. It's on page 558. Let's look at this concept check. All right, so it's the last thing in section 16.3. All right, so we have this beaker and a base B is placed into the beaker and we end up with what's there. All right, so let's write an ionization constant for the reaction. And first let's answer the question. Is it a weak base or a strong base?
Strong?
How do you know? From looking at the contents of the beaker.
Because of the, what is it, the BH? How many are
Say again?
in there? Because the BH, how many are in there?
Anybody else? I'm not saying if that's right or wrong. Do people agree with it? Well, let's see. If it's a strong base, when you put the strong base into water, there's none of it left, right? Because it will all react with the water. That's the definition of a strong base or a strong acid. Remember, a strong acid, you put it into water, it completely ionizes or dissociates. A strong base, when you put it into water, it completely ionizes or dissociates. Do we have any of the original base left in that beaker?
Yeah.
Yes, we do. So that tells us this is not a strong base, but a weak base.
Oh, okay.
Okay? That
Okay.
tells us it's a weak base. Now, so we have actually, I wish that one problem, the quinine, I wish I had not written it as HA. You should have written it like this. Now that I think it's been a while since I've done these, I wasn't thinking. So here's the base. It's going to react with water. That's going to give us, let me write it smaller. Here's the base, B. That's what we should have used in that quinine problem. All right, I wrote HA. We shouldn't have written HA. We should have just written B for base. Plus water gives us, double-headed arrow, BH plus OH minus. Notice in the beaker, we see this, we see this, we see this. All right, so here's the ionization reaction. And we see all three of these, so it is in fact a weak base. Remember, if it was a strong base, we would not see any of this in that beaker at all. We would only see this and this. Okay? Everybody good here? Everybody good? All right, let me assign you some problems here. Actually, I'm going to stop recording here.